introduce Markus Müller, who is giving a talk on fault-tolerant quantum computing. He's a professor at the Institute of Quantum Information at the RWTH in Aachen. He did his PhD in Innsbruck, right? And then went for a postdoc in Madrid. Yeah. After which he went to the UK at Swansea University, where he did professorship actually, right? And then after that he went to RWTH Aachen to have a full professorship, and now he's working on every kinds of aspects related to quantum information. One of them being fault-tolerant quantum computing, and I'm really much looking forward to your talk.
Thank you very much for the kind introduction, and thanks for the invitation. It's really great to be here in person and to have been already over the last days here with you. Yeah, I want to speak today about fault-tolerant quantum computing. That's, as you mentioned, not everything that we are doing in my group. So my background is mostly in atomic physics, atoms, ions, but we've also recently moved into collaborations on superconducting qubits. This is a little bit of an overview of the research lines. So we are interested in designing schemes for quantum computation, for quantum error correction, both, as you will see, from a theoretical point of view, but then also in very close collaboration with experimentalists. And then other topics that I will not be speaking about concern quantum simulation, in particular of open systems or systems with topological order, or quantum neural networks and quantum machine learning that we are also investigating in my research group. But what I want to do is today give you a lecture about quantum error correction. You have already gotten an introduction by Victor Albert earlier this week, and I want to build on this, starting with a brief recap. Sorry. And then speaking about one aspect that is particularly important, and that is the one of quantum fault tolerance. And I hope that you will get a feeling and an understanding of what that is. So over the last days, you've already heard a lot about, let's say, the NISQ area of quantum computation, if you like, where we have our physical hardware. You've heard about different platforms. And then there are some techniques, such as dynamical decoupling, noise mitigation, and so on, in order to squeeze out, if you like, the best of these systems that you can, and then hopefully be able to use them for some user-defined practical applications. And what I want to do in this lecture is take you to this mysterious fault-tolerant land that you've heard a lot about, namely by then giving you a perspective on what we actually will need in the mid and long term to build really scalable and fault-tolerant quantum computers. And what you see here is that there's then, if you want to look at this in the systematic or schematic structure, there's then additional layers of conceptual layers and also from a practical control standpoint, namely of how we can work instead of with physical qubits, with so-called logical qubits that I will be introducing to you, doing error correction on them, trying to preserve quantum states, but eventually, as I will show you, not only to keep quantum states alive with quantum error correction, but actually do quantum computations on these logical qubits. Because in the end, what we want is to run quantum algorithms not at the level of physical qubits, but at the level of logical qubits. And this brings me, say, to the outline of my talk. So I want to start with a brief recap of some of the concepts that you've been seeing in various talks, just to bring everybody on the same page, and then introduce one particular class of quantum error correcting codes. To a certain extent, once again, you have seen some of this already in Christopher's talk on the surface code earlier this week, but still I want to kind of go through this slowly and give you a theory introduction to that. Before I will then move on and talk about these two challenges of doing fault-tolerant error correction to keep states alive, but also fault-tolerant logical quantum gates to process really encoded information. And then in the end of the lecture, I want to speak a bit about scalability. I'm not an experimentalist, but although working with experimental colleagues, but here my idea is more to give you an idea of what the different conceptual approaches are of how one might build a scalable fault-tolerant quantum processor, and some of the schemes that will come to life in there. All right. Yeah, with that, let's get started with the recap. And as I mentioned already, please feel free to just interrupt me at any point. I'm happy to go into details. And if something's unclear, just kind of slow me down, and I'm happy to answer questions. All right, so why do we need error correction at all? Well, all the quantum processor platforms you've seen so far, they suffer unavoidably from the coupling of the system that encodes our quantum data to the environment. What you see here is an example of, for instance, the effect of magnetic fluctuations as they take place in the trapped ion quantum processor, but also other architectures. And the effect is when we start with a pure superposition state, then under this dephasing, for instance, or under these magnetic field fluctuations, we will pick up different dynamical phases, and those are unknown to us. And that will lead then, after a certain time, to the loss of the relative phase information, so that we end up here, for instance, in a classical mixture where the phase information of the state is lost. And this is an example of phase flip errors, where we can then now think of the generators, say sigma z operators, inducing these phase flips. And similarly, they are also, like in the classical case, bit flip errors that flip our state from 0 to 1 and vice versa. And then there are in reality more errors. I only speak a little bit about those, but not a lot. Namely, the problem of leakage, where your qubit leave the two-dimensional computational subspace, ending up in other states, or also in some architectures, as the photonic architecture you just heard about, where your entire qubits can get lost, and that is what is known as qubit loss. Then the noise models in reality are more complicated than what we theorists usually try to solve. In the sense that one has not simple, incoherent, uncorrelated noise, but one has typically spatial and temporal correlations. And that's also something that one has to take into account when dealing with these error sources and to protect the information reliably. All right, here you've just a quick reminder of the simplest three-qubit code that has been introduced on Tuesday, I think. Where the idea is to store information not in single physical qubits, but in these global superpositions we call logical qubit. And just as a quick reminder, the idea here was that we can now store information in this two-dimensional subspace, the three-qubit Hilbert space that I've here kind of drawn as this box, if you like. And the idea is that if errors happen, we can measure so-called stabilizer operators. So this would be here two-body correlation operators between, in this case, the first and the second qubit, and the second and the third qubit. And if an error happens, say here on the first qubit, by measuring these correlation operators, we can find out about the effect of the errors. Here, for instance, then seeing that the parity between the first and the second qubit has changed here to an odd parity. One is up, one is down. But we do not get information about the logical states, but just about the parity. And similarly, then the Z2, Z3 would indicate us here that here, the second and the third qubit, they are still in an even parity state. And then based on this so-called error syndrome information, we can then make a guess without collapsing the logical quantum states, without learning about alpha and beta, and apply a suitable correction, which in that case would simply amount to, based on this information, to apply an X flip, either by doing a feedback on our quantum register or kind of keeping this in our minds and do this on a software level, simply keeping in mind that we think that there has been an X error. Then what we have, besides these so-called stabilizer operators, we have also logical operators, and those are the generalizations of the physical Pauli operators that you know, X and Z. And what you see here for the three-qubit code, for instance, we can use as logical X operator the operator that acts with X on all three physical qubits. That obviously flips the logical 0 state all in 0 to all in 1, and vice versa. And we can choose a logical Z operator as the product of Pauli Z matrices. Each Pauli matrix Z applies a -1 to the 1 state, so that if you apply this to all three qubits in 0, nothing happens. If we apply it to the 1-1-1 state, we pick up 3 minus signs, so we get overall a minus sign. And that's exactly like the effect that we need. And what you see is that these logical operators, they anti-commute here, because the Pauli matrices anti-commute with each other, but they share 3. So overall, these two operators anti-commute, and they behave really at the logical level as the physical Pauli matrices that we know. Okay. Seen earlier is then kind of the conceptual setup of an error correcting code, where we would start with here a physical basis or a physical state, alpha 0 plus beta 1, say. And then we encode this state now collectively in our register, in our little quantum error correcting code here. For this basic code, this can be done simply with 2 C0 gates. And then the idea is that if now errors, in this case bit flips, can happen on one or several of these data qubit registers, then we can detect those, as I explained, by measuring the error syndrome. And this is being done by a coupling a subset of the data qubits here, the first and the second, to an ancilla qubit that measures parity here Z1, Z2 by coupling it to this ancilla qubit, where we would then exactly get this information. If, say, here an X error happens, this would be visible by here a -1 measurement of this parity operator that realizes a measurement of Z1, Z2, and then whereas Z2 and Z3, they would still be in an even parity state indicated by a +1 outcome of this measurement. And this syndrome information, as I mentioned, is then used to apply a suitable correction in hardware or software to the system. All right, so how good does this little work? Let's look at this and assume a very simple noise model, namely the same as used in classical information. Assume that each of our qubits can suffer a bit flip with the probability p, and with the probability 1 minus p does not suffer a bit flip. So what's then the overall probability that if we encode our information in the 3-qubit code, that we will be able to correct the occurrence of an error or more errors? So let's look at this. On our most lucky day at experimentalists, nothing will happen on our quantum register. And that happens with the probability 1 minus p cubed. No error on any of the 3 qubits. Then, however, we can be in the situation, if we have one error, say here on the first qubit, and no error on the other qubits, that would happen with the probability p times 1 minus p squared on the other two. And then you see there are 3 of these configurations so that we get this combinatorial factor. And if you now work this out, then you see that the probability that we have either no error, that's trivially correctable, or one error where we will get to the right correction, the probability will be given by this 1 minus 3p squared, and then another higher order term that goes with p cubed. Similarly, if we have 2 or 3 errors happening on the 3-qubit code, then we cannot correct this error, and this is given by this failure probability then that is in leading order 3p squared. All right, and if we now ask ourselves, okay, should we now encode information in a single physical qubit or use the 3-qubit code? We should compare the 3-qubit code performance, or the logical correction probability, to the probability that if we store the information in a single physical qubit, nothing happens, and that is then under the same noise model simply given by 1 minus p. That this single qubit which carries all the information is not suffering an error. And now we can put the two things together and compare them. So what I've shown here is the straight line, that's 1 minus p for the physical qubit. Here we have indicated the single qubit error rate at which bit flips occur on all of our qubits. And now you see that here we have this quadratic behavior of the correction probability. And then for not too large error probabilities of the physical qubits, now you see that the probability that they can actually correct using the 3-qubit code is larger than if we store the information in a single physical qubit. So that's here by this, if you like, advantage regime, so to say, where it's actually better to use the 3-qubit code as compared to the physical qubit code. Unfortunately, you see that's not quite 1. There's still a finite probability to have error, an uncorrectable error, since we cannot correct 2 or 3 errors in this system. The code is simply too small and too simple. So what can we do? Well, we can then increase the system size, going from, say, 3 qubits to 5 qubits, and encode in a similar way here now the information in these logical states, where you, if you look at that and would have to guess, what would you guess has happened most likely on the system? On which qubits did we have errors?
For the majority.
Yeah, so concretely, which of the qubits 1, 2, 3, 4, 5 would have suffered an error? What's your guess?
3 and
on 3 and 4, exactly, yes, yeah. So, and this is something that we would, that's more likely, right, as compared to the possibility of having an error on qubits 1, 2, and 5, at least if p is not large. Yeah, when we go for kind of the majority, or we are looking at what is the error configuration that is more likely, and that is typically for low error weights, the one that is a smaller weight, acting on fewer qubits. Indeed, and then you see here, okay, here we can correct 2 errors. If we have 3 errors, we would be misled, right? If here now, you know, we had actually an error occurring on qubits 1, 2, and 5, we would apply a correction on 3 and 4, and thereby overall induce a logical bit flip. So you see, with that, we can correct up to half or 1 qubit less than half of the length of our 1D repetition code. And now, that means if you now increase the system size, the probability of having an uncorrectable error goes down, and this correction probability gets closer to 1, and this really develops into a sharp phase transition, if you like. So how can we see this a little bit more conceptually of how this phase transition emerges? So one way is simply to take this string and make it larger and larger, but there's also another technique that is called concatenation of codes that can be used to increase the robustness of information stored. And the idea is a little bit shown here, yeah, like with these Russian dolls. The idea is to encode information in a code, and then take each of these qubits, again, encode it using a code, and so on. And we can play this then up to the desired number of levels or concatenations of these shells or layers, if you like. So let's think this through for a second for this 3-qubit code. Yeah? We have seen that if we just take our physical qubit and encode it in 3 qubits, that the leading order of the failure probability was 3p squared, and then there was actually a minus 2p cubed term that I neglect here. So it's smaller than 3p squared. Now, if we take each, as I said, each of these 3 qubits, and again encode it in this example here using the same 3-qubit code, using the 9 physical, now the idea is that this is we can now use this effective probability of that we have after encoding it in one code, and use that as the probability we now put in when we look at the logical failure probability at the next level. So that means at the second level we have again a 3p squared probability, but now the p at the next level can be substituted by the 3p squared of the previous level. And then we can iterate this, and you see here that we get a logical overall failure probability after L levels of combinations that goes like 3p to the power of 2 to the L. And now what you see here is that then if our physical error probability for this little estimate here is lower than a third, then 3 times p is smaller than 1, and then the overall failure probability goes exponentially down to 0. That means our chance to correct gets exponentially fast to 1. And this is what is would be now here a lower bound for the critical error threshold, below which we can actually reliably correct errors. Now one has to think a bit more carefully. What you see here is, well, it's also a costly procedure, right? We start with 3 qubits, and then we do 9 qubits, and then we have 27, 81, so this explodes. You see the number of physical qubits grows exponentially using the concatenation approach, but luckily the logical failure rate goes down double exponentially. It goes down not just with 3p to something that is of the order of L, but it goes down with 2 to the L. So that means the logical failure rate drops actually double exponentially. That means faster than our physical qubits, number of physical qubits grows. All right, so to make this a little bit more concrete, imagine that we have done these 2 layers of concatenation. We have these 4 errors happening, 4 bit flips on our register of 9 qubits. What would you say? Is that an error that would be correctable or not? Okay, so that's a okay. One argument is, okay, here we have 9 qubits, so 4 qubits are less than the majority. Yeah. It's more than a third, yeah. So yeah. So who is right? Question, yeah. Or is it actually perhaps a little more subtle? So imagine that we now look at these 3 qubits, right? And now we would be doing a correction on this sub-block here. So in this case here, that would be an uncorrectable error. So that means at this previous layer, this would amount to a logical error here on this intermediate layer qubit, so to say. Whereas these single errors, they will be corrected so that we have here, let's say at this intermediate layer, 2 of them in a right state. And then, you see of this intermediate block, then again, you think this through, and you see that this single error would be still correctable, so that we can get back. Yeah. So it's a little bit more subtle. So imagine that we had here these qubit errors here on 2 on this block and 2 on this block. Then we would not have, using this strategy, a correctable situation. Yeah, that's at least a very basic argument of how this works. All right. Yeah, so with that, I wanted to kind of give you an idea of how concatenation works and ask whether you have any questions up to this point. Yeah.
So you kind of have a trade-off, right? You can make a bigger code and less concatenation, or more concatenation and smaller code. Is that like an optimum?
Yes, I mean, exactly. So I've been here a bit generic because I didn't really specify what kind of code we use. Yeah. So it depends on your noise sources, what kind of codes you should be using. And what I want to show you in the following is that this idea of concatenation is nice theoretically. You can prove that error correction works, but there's a much more experimentally suitable approach using a different type of increasing the robustness. Yeah. Okay, so if there are no further questions at this point, then let's look at now this from a little bit more conceptual point of view. So what we've seen is that we have encoded a single qubit now in a code here, so using a bunch of ancillas. What we then walked through is that if errors happen on the system, and we do a round of error correction under which conditions we can or cannot correct the errors. But now, if we think a little bit more ahead, what we have is actually then a register of several of these logical qubits on which we would run some kind of error correction. And then, as I mentioned earlier, we also want to do logical gates, to which I come a little bit later, on the individual logical qubits, single qubit logic gates, but we also want then to entangle logical qubits by here, say, an entangling gate between these 2 logical qubits, 1 and 2, and then run another round of error correction and so on, and in the end, after our logical computation, read out the result. And what I've presented to you is a very simplified version, right? We assumed that our encoding of the state was perfect. We could read out the syndrome perfectly. And the only place where errors were allowed were on the data qubits, and everything else was allowed to be perfect. Right? And what we have to do is to refine these assumptions to go to something more realistic. And in essence, so to say, it means that every component here can fail. Right? There can be errors already in the process. There can be errors in the quantum error correction cycles themselves and also in the logical gates. And what we'll be seeing is that one has to think about fault-tolerant procedures of how to realize all these subroutines. And the definition of fault tolerance here is as follows. A certain quantum circuit, or as shown here, is fault tolerant against t errors, where t is an integer, 1, 2, 3, something like that. If we can allow for up to t failures, and the important thing is that these failures can happen at various points, and that they amount only to t errors in each of the code blocks. That means on each of the logical qubits. So an example, what we want is, and we will see how this works, is that if here a single error happens here, say on this first logical qubit, we have to make sure that this does not result, if we apply a gate operation afterwards, a logical one, that this propagates into, say, 2 errors. That would mean violating this fault tolerance condition. So, and the promise is, if we can manage to construct the procedures for error correction itself and for the logic gates in a way that this condition is fulfilled, then this concatenation argument works, right? Where we used the fact that a single error remained correctable, right? We had the example of the 3-qubit code. Single errors were correctable, 2 errors were not. If we manage that single errors do not spread out into more than single, that is kind of what will allow us then to carry through this argument and then to prove the existence of a threshold. And this is actually what is the quantum threshold theorem, if you like, namely that if one works with such fault-tolerant procedures, then one can prove by essentially doing this concatenation argument, which is technically more challenging, but it's exactly this idea, that there exists a physical error probability, a finite critical value for the physical error rates at which these constitute components fail, and one can then prove that the logical error rate can be suppressed exponentially, and that means that one can now, if under these conditions, run, in principle, quantum computations efficiently on the logical level. So that's, on the one hand, that's great news, no? Because it proves that it's worthwhile building a quantum computer. On the other hand, the fine print is that if one uses this approach, the threshold rate, that means this critical failure rate by using this concatenation type of argument is very low. It's on the order of 10 to the minus 5 to 10 to the minus 6. So, I mean, to understand what this number means, it means that an experimentalist has to do a gate operation 1,000,000 times before it's allowed to fail a single time. So that's really tough. And that is why there's an alternative that I want to introduce to you, namely topological quantum error correcting codes. And besides the fancy word of topology, the main point is that we will be seeing that the error rate under which this works are much more experimentally friendly. Okay, so first in a qualitative picture, what is a topology? Well, it's some global features that are robust under local deformations or perturbations of your system. So what you see here is a cup, and I can deform this locally, continuously without breaking this object into this donut. And what you see here is that those two objects, they share this global property, namely that they have one hole in the middle. And now the idea of topological quantum error correcting codes is to use a many-body quantum system, typically a spin system, locally either on single physical qubits here indicated by lines or perhaps on small regions, but not extending over the entire system, that then one can protect this globally encoded information against local noise. And as you'll be seeing, that will lead here then to thresholds that are typically 2 to 3 orders of magnitude larger and at error rates that are already achievable in various experimental platforms. And that means that that is one of the approaches, as I want to convince you, where fault-tolerant quantum computing might be possible, not only in principle, but that's a way to go in practice. All right, then let's introduce the system that is perhaps the most well-known code, the only one, as you will see, but it's the one that was proposed first by Alexei Kitaev. And what you see here is now a square lattice, where the blue dots correspond to the qubits that sit on the edges of a lattice. And the idea is now that we introduce, like for our 3-qubit repetition code, also stabilizer check operators that allow us to detect the presence or occurrence of errors. And what we introduce are here 4-qubit Z-type stabilizers that act on 4 qubits sitting here around a plaquette, and this on the entire lattice. And similarly, we'll be introducing X-type vertex operators that act on 4 qubits that sit around the vertices here on the 4 edges that connect to one vertex of the lattice. And the idea is, as before, we can use these Z-type stabilizers to detect the occurrence of bit flip errors, and vice versa, the X-type stabilizers to detect the presence of Z-type errors on the system. Now, what you can easily verify is that all these stabilizer operators commute, so I can measure them without disturbing the measurement of others. As you can verify here is they either don't share any qubits, as in these two examples, or if you look at this plaquette and this vertex operator, they share here 2 qubits, where kind of the Pauli X and Z meet at 2 positions. You pick up 2 minus signs, so overall, these 4-qubit stabilizers, they all commute. The idea is, like for the 3-qubit code, that we want to store a logical relation in the joint +1 eigenspace of all these X and Z type stabilizers on the lattice. That is what, again, is the code space where our logical states live. Now, how can we then in this code space define logical qubits? For that, we have to lift the degeneracy of this code space. And what I want to look at first here is a situation in which I put this square lattice on a torus, or it's another word of saying simply, let me look at the system with periodic boundary conditions, right? Where these 3 qubits here would be the same ones like here, and identify this upper boundary with a lower boundary. So wrap this on a torus. Okay, and what we can now find are operators, like the logical Z and X operator that we had earlier, that commute with these stabilizers, but they are independent, so I cannot build those from stabilizers. And what I introduce here are Z and X type string operators. So what you see here is a Z string operator that acts on these 3 qubits here, and for instance, this X string operator that again acts on these 1, 2, 3, and that's the same qubit again. Similarly, can introduce string operators in the other direction, now wrapping around, let's say, the whole of the, or the handle of the torus here, again of Z and X type. So why did I choose them like that? Well, if you look at, for instance, this X string operator acting with Pauli X operators on these qubits on this line, it trivially commutes with all vertex operators that are Pauli X. But it also commutes with all the Z-type plaquette operators. Because, for instance, here you look at this plaquette and you see this operator shares 2 qubits with a plaquette. It enters a plaquette and goes through a plaquette. So that means these are operators that commute with the stabilizers. So meaning we can encode our logical qubit in the code space without bringing the system out of the code space and introducing errors. Now, why are these good logical Z and X operators? Let's look, for instance, at this Z-type string operator here, acting with on 3 Z-type qubits, and this X-type string operator that goes here along this vertical direction. Why would you say that these are valid logical Z and X? Yeah?
Because the commutation relation is according to X, and that we would expect it if they share 1 qubit.
Exactly. They just meet at this 1 qubit. They anti-commute the Paulis. And that's why at the logical level, this Z string operator anti-commutes with the X operator. Indeed. And the same is true for this X2 here and the Z2. They cross here at this 1 qubit. And then although it looks as if, say, this Z2 operator crosses the X, say the Z1, they do not share any qubits. Yeah? They go here through the same vertex or the same plaquette. But this is exactly why they, if they belong to the same qubit, they anti-commute. They form a valid set of logical operators. And if they are operators acting on different logical qubits, they commute, as should also the Pauli operators on physical qubits do. All right. So with that, we have our logical operators that corresponds to string operators going around the 2 non-trivial directions of the torus. Now, I said earlier that we can now use these stabilizers to detect the presence of errors. And what you see here is, for instance, if there's a bit flip on this physical qubit happening, and we measure the Z stabilizers on all of the lattice, then we will have all stabilizers in +1 except the 2 stabilizers that are adjacent to this qubit and involve this black qubit here where a bit flip has happened. So we will be seeing this as, if you like, as excitations or localized excitations, shown as these red dots. And this would be our syndrome information on the 2D square lattice, from which we have to make a guess of what the best possible correction is. Okay, so let's then try to do this. Yeah? And some of you might still know this whack-a-mole game. And this is a bit, in a nutshell, what topological error correction amounts to. Yeah? So we have this lattice, where ideally we don't want to have any of these moles, but then nature introduces errors. These excitations, the moles pop up. And our task as experimentalists doing error correction is to identify the position of these moles and hit them kind of with a suitable hammer to bring them back into their holes and thereby remove the errors quickly enough before they can kind of lead to a logical error. So let's see how this works. Yeah. So that would be our qubit lattice. Yeah, the yellow points are the qubits on which errors can happen. So if we now see here, let's say on these two plaquettes, a negative stabilizer expectation value when we measure this four-body operator here and there, and on all the others, we would be seeing a +1. Now we would use this information to make a guess of what has likely happened, and you probably all agree that it will have very likely been a bit flip error on this qubit. And this is then what we would, if that's the case, right? The error has taken our system out of this code space. Yeah, you can think of this as an excitation. And now our recovery operation, what it does is it hits here this qubit here with a sigma x, and thereby it merges these two excitations, bringing the two moles or the two excitations back into their hole. And then you see that the error and our recovery operation applying a sigma x, like for the 3-qubit code, sigma x squared is identity, so we definitely get back to the same logical state in our code space in which we can encode two logical qubits. Now, what might have happened if we see two excitations at these two positions on the lattice? What do you think is a likely error that can have caused this syndrome?
There could be two errors in the middle, and then that's why the middle one wouldn't be because of the minus.
Exactly. Yes, that's a very good guess. So most likely there have been two errors here. Then this will leave this stabilizer in a -1 state, and this one as well. And as you correctly said, since I have an x here and there, that's two x's that commute with the four-body z operator so that this parity is even. Yeah, so you can also think of this as being a pair of errors created by one error, and then a second error makes this hop to a neighboring site. Okay, so if that's the case and we undo this, then perfectly fine. Again, the error cancels out with our correction. But now this thing is on a torus. And there's one other error situation, which is only slightly less likely, right? We could also have a situation where the error was 3 qubits, bit flips, yeah, here, that's the same qubit, and there. So this 3-qubit string here. And in this case, what you see is, if that was the actual error, one here on these three, and our correction applies those, we'll bring those excitations back, but now the error plus our correction, it corresponds to a string operator. So that means we get back to the code space, but now we've introduced, without noticing, a logical bit flip operator that has changed our logical information, and there the error correction has failed. Right, so these are the situations that lead to a correction or a failure. Whenever we enclose a logical loop operator, then the error correction has failed. And this is a bit oh, sorry, that's quite loud. This is again, here a bit of how one can see this. I mean, it's a thing one can learn. And over the years, let's say, there have been different strategy being developed to deal with the errors. And like here, the cat, it becomes smarter and smarter to deal with errors. There have been better and better decoders developed. Yeah? So what is the idea? So if we have, say, this surface code that we just looked at, and we look at the noise model that we just were playing with, yeah, where you say everything is perfect, the only errors we allow are bit and phase flips that happen on the lattice, then one can show that one can correct up to almost 11% of bit flips, look at the lattice, come up with a suitable correction, and with a probability close to 1, one will remove these excitations without inducing a logical error. So that's the threshold under the noise model for this toric code when we have only bit and phase flip errors. Now this is obviously not very realistic, because if we want to measure these stabilizers, we have to couple, say, these 4 qubits here to an ancilla qubit with a series of C0 gates to map this 4-qubit stabilizer information onto an ancilla qubit. And now what one can do as a simple model, and that's known as circuit model, is one can assume that each of these components, qubit initialization, single qubit gates, C0 gates, and measurements, they can fail with a probability of p. And then you can ask, okay, how large may this P still be, so that we can still correct with a unit probability or close to unity. And that's what one then finds this famous 1% threshold for the toric and surface code. And that is the kind of the 10 to the minus 2 level under realistic circuit noise that makes the surface code and other topological codes an attractive candidate for actual quantum error correction in practice. Okay, and as I showed you earlier, so this is much higher than the typical thresholds one gets when one uses this concatenated approach. And the reason why this is higher, I mean, there are many reasons, but one is, for instance, what you see is that you have a local lattice structure that can be embedded in 2D, and the only thing we have to do is, but it's better than in concatenated codes, is to do local operations. We have to measure stabilizers locally of groups of qubits that are close to each other, whereas in this concatenated structure, one has a tree structure where one, in principle, has to measure correlations between qubits that are arbitrarily far apart from each other. In most architectures, this can't be done. We have to swap information, do swap gates to bring qubits together, measure them, and swap them back. And this overhead is a little bit what is behind this much worse thresholds using a concatenated approach. All right, now obviously I said this is nice for experiments. If you're an experimentalist and I come to you as a theorist and say, I have this toric code, can you please build it? They say, yeah, sure, in 20 years, speak again. Good news is that one doesn't need this toric code structure, but there are planar codes, the surface of the Kitaev's code and others that I showed you. And what I want to show you here is how one can map this now onto a truly planar architecture. So you see here now again a qubit lattice. Here we do not have periodic boundary conditions, so it's really planar. This is not the same qubit as this one. And what you see is that in the bulk, we have the same stabilizer structure, 4 qubit Z stabilizers, 4 qubit X stabilizers. Just at the boundary, we have now this open 3 qubit Z stabilizers here. And on the left, we have this 3 qubit amputated, if you like, X-type stabilizers. Right, and now we can again look for logical operators. We can again introduce here a Z-type string operator going from the top to the bottom. And here an X-type operator going through the plaquettes from the left to the right. You can verify that they commute with the stabilizers. And as you see, they again also cross in a single point. So it's valid logical operators. And now you might ask, okay, where's now the topology? Yeah, here the topology was in these non-contractible loops. Here it's about non-contractible strings that end on, or start here, say, on this smooth boundary where you have this X stabilizer and ends on another smooth boundary. So that's a string that goes from left to right. And similarly, the Z-type operator here would start at this rough boundary, or spiky boundary, if you like, and on one boundary and going down to the other. Then you again see that it's not dependent on how exactly choose the form of these string operators. I'm free to say I have this rough boundary and this rough boundary here. I can have a logical operator. That would be my X logical. I can have a Z logical that cross here in a single point, or equally, I could have chosen, something more fancy, whatever, right? Like that. And now if I've done this correctly, and you count at how many points those cross, this would again be an odd number of points. So I can deform these strings, and they will keep their anti-commutation relation. And they are all different equivalent logical operators, so we have a bit of choice there. All right, so with that, we are almost there. It's already much nicer for experiment. Now what one can do is one can look at this code slightly differently. I can kind of take these plaquettes here and introduce those as yellow four-body operators, and then each vertex operator, I could introduce those as brown X-type operators. It's just a different visualization. That's the same lattice I've up here. Now what one can show is one can even chop off some more qubits. Here at the boundaries, or at the corners, they are not really needed. And then one ends up here with a surface code where one has it has just 9 qubits here for this example, yeah. And if you rotate this by 45 degrees, then you get this lattice here, where you have in the bulk exactly this 4-qubit X and Z type stabilizer structure, and then some 2-weight stabilizers at the boundary. And this is the code that Christopher Eichler introduced to you and explained how that worked in an experiment. And that's the smallest version of surface code, so now as a planar version of the toric code, that involves 9 data qubits. And then in order to measure each of these 4 X-type and the 4 Z-type stabilizers, one has 1 ancillary qubit, so 9 plus 8, that's 17, and that's why this code is also known as the surface 17 code. Okay, any questions up to this point?
Why you need to add additional qubits to measure? Is it just why can't we just measure without additional qubits, ancillary qubits?
Well, and the problem is always if we have to map this 4-body information onto an ancillary qubit, because if we measure the data qubits directly, we collapse the data state. Yeah, so that's the trick. We have to get this indirect information about the parity of, say, these 4 qubits without learning the state of the individual qubits, which we would do if we project them individually. That's why we need the ancillars. All right. Good. Then let's continue, perhaps for a few more minutes before the break, and get started with now discussing of how we can do the quantum error correction that I kind of introduced to you now fault-tolerantly. And for the moment, we focus on the memory challenge. That means keeping a quantum state alive. So here you see the surface 17 code that I just introduced to you. On the right-hand side, you see another basic quantum error correcting code, the Steen code, that is formed of 7 physical qubits, and it's also at the same time the smallest representative of the 2D color codes, which is another class of topological quantum error correcting codes. And here is that here we have 7 physical qubits that are arranged on these 3 plaquettes. The colors are just a labeling index, yeah, to make language easy. They don't change. It's not a degree of freedom, really. And what we have on each of the plaquettes are Z-type and X-type stabilizers. We have only plaquette operators in this class of codes. And what you see is, again, they commute with each other. They share qubits. They are neighboring plaquettes here. And we have 7 data qubits, 6 stabilizers. That means there's 1 degree of freedom left that allows you to encode 1 logical qubit in this 7-qubit color code. All right. Then as logical operators, we can choose the operator that acts with all 7 qubits as a Z operator. And similarly, the logical bit flip operator can be chosen as to act on all 7 X or qubits with X. You see it's an odd number, so they anti-commute, and they commute with all the 4-body operators. So these are valid logical operators. We can, however, also choose a logical operator that has lower weight, because we can, let's say, start with this 7-body Z operator, but now deform it by applying a stabilizer, because any logical state is an eigenstate of the stabilizers. So if we take this weight 7 operator and multiply it, say, with this blue ZZZ operator, those qubits cancel out, and we end up with just a weight 3 operator here, living on this boundary on qubits 1, 4, and 7. All right, and yeah, with that, then let's have a quick look of how we implemented this some years ago, this code, in a trapped ion quantum computer that was introduced by Cornelius and others earlier this week. Where you see again the Paul trap with a string of trapped ions, each of them encoding a physical qubit in 2 metastable electronic states that can be manipulated here by driving single qubit gate operations and using the vibrational modes in order to do entangling operations between any pair of qubits in this 1-dimensional string. So we have a quantum computer with an all-to-all connectivity between the qubits, and that will be important for what you will be seeing. Okay, so let's take this color code, kind of take this 2D structure, map it onto the 1-dimensional chain, and then what we want to do first is to encode the logical qubit, meaning that we have to prepare it in a +1 eigenstate of all 6 stabilizers. We can start here with a simple product state of the 7 qubits. That is already an eigenstate of all Z-type stabilizers. Yeah? Simply means we have an even parity of the qubits on each of the packets. And then what we did some years ago is then to use some global entangling gates, which we acted on subsets of qubits. Say here this first 4 qubits of a plaquette with a so-called Mermer-Sørensen entangling ion gate, to bring this also into +1 eigenstates of this X-type stabilizer here, then move to the next plaquette acting on those 4 qubits and on those 4 qubits. And with that, we initialize the system in the code space and with a logical 0 eigenstate. And ideally, as I explained to you, we would have liked to see here a feature where we have +1 eigen values on all plaquettes, and this is what we saw roughly in this experiment. However, you see this doesn't really go up to 1, but stays at a lower value. But still, qualitatively, one could see this feature. And now, imagine that you measure the 6 stabilizers, and that's what you see here on the right, and you now find 2 of the stabilizers, say this red stabilizers, the red Z-type stabilizer and the blue Z-type stabilizer in the -1 eigenstate. So what would you as an experimentalist now think? What is the most likely error that has happened on the system? Qubit 2, yes, yeah, because the green plaquette looks fine, right, and this is involved in those 2. And what type of error would you guess has happened on qubit 2?
A bit flip?
A bit flip, yes, because the bit flips anti-commute with the Z stabilizers, right? So that's exactly what this syndrome corresponds to. All right, that's the example I showed up here. So now to just get going a bit. So if the blue Z, or no, that's the blue X stabilizers is negative, all others are up, what would be your guess in that case? Phase flip on 5, exactly. That flips here this blue plaquette, leaves the red and green invariant. And for this pattern, looks nasty, but what do you think? The Y on 3, exactly. Because a Y error is just the product of X and Z. All right, so we see it's simultaneously flipping all the 3 X stabilizers and all the 3 Z stabilizers. Yeah, so now you have been kind of doing the simplest way of decoding, and that would be the error correction table that one would apply based on this measured syndrome information in order to correct the states. Although you see here, this experiment was a demonstration. It was not at the level where protecting information could be beneficially done in the system, but we induced at that point the errors at purpose here by exactly shining in laser pulses, and obviously we want to push this to the limit where it becomes useful for the natural noise occurring on the system. As a last comment, if we had, say, this single error and then we have a second error here, that would again lead to a syndrome where we would only see this plaquette. In this case, we would think it was a Z error here, but then you see whenever you have 2 errors on the system, that will amount to an uncorrectable error, because now the errors here in our correction, we think it was on Z1, will lead to a logical operator that lives on this boundary. It's only a distance 3 code where it's guaranteed that we can correct 1 arbitrary error, and that's kind of what I try to convince you of. But you also see that for this Steen code, any 2-qubit error, where you have 2 errors of the same type anywhere on the 7 qubits, will lead to a logical error. And that's what we have to prevent from happening. And this is where we want to look at after the break. I just leave this transparency up here with a little exercise for you. Namely, this was the encoding circuit that we used for encoding a single physical qubit in the 3-qubit code. And now the question is, and you might want to work this out over the break, is what happens if actually during this encoding procedure you have a single bit flip happening, say here between the first and second C0 gate. Yeah? So what is the state that you get out here, and what would happen if you then run the quantum error correction cycle as we discussed? All right, so it's a very simple exercise. Have a look at that, and then we'll continue after the break with a discussion of what the issue with these errors happening during the actual components is and how we can deal with them in That will lead us to now practical realizations of this fault-tolerant promise that I introduced you earlier. All right, any questions up to this point? Yes?
Very tiny annoying one, but I've heard the question, should I like to work on quantum error correction or fault tolerance? And in my head, it's a means to an end. So what is the question when people are asking something like that?
Whether you want to work on error correction or?
Yeah, it's like, so are you interested in like the error correction part or the fault tolerance part? You know, like it's just, why are you separating these two things? Saying that there's a lecture on quantum error correction and a lecture on fault tolerance. So like,
Well, they're not really separated. Let's say fault-tolerant way is the right way of doing the error correction, if you like, and we'll see what that means in practice. Yeah. So far we've introduced the codes. You've seen that the codes, they provide you with a promise. Right? This 7-qubit code promises you, as long as there's not more than a single error, you will be able to correct this. But now we have to kind of find the right circuit engineering to use that capability of that code without screwing it up ourselves, so to say. Yeah, that's what we will see. Yeah. All right, then I would suggest we have a short break here and reconvene roughly at 1:15 or so.
I have a question. So,
Yeah.
from your perspective, because I think that always bothers me when I see like these error correction diagrams is like, oh yeah, a bit of this, like you assume like perfect C-nodes between your physical qubits and B and C-less. Of course, that's not the case. And like, so from your perspective, like, how's it gonna be like in the next 5 years if the gates are still like
absolutely. No, and I will show you after the break. So we will now give up this assumption, and that's the first step of giving up this assumption. Yeah. You can think of this problem, right? We have, in principle, a code that allows us to correct a single bit flip error, but we've done the encoding now in a way where a single error in the encoding directly leads to a logical failure. And this one can understand here now a little bit more systematically by an operator identity. So this is not only happening when you act this on this particular input state, but actually this is an operator identity. So whenever you have an X error or gate or happening before a C0 gate, this error, although the C0 gate is perfect, right? The error will propagate through this gate. So it's equivalent to having the gate and afterwards the two errors. So you can think of this as there is an error on the control qubit, and by talking to the target qubit gets infected. Yeah? This is the error spreading, where you see here a bit flip error spreads forward onto the target qubit of a controlled NOT gate. And so this is this identity that I wrote down. One can now also ask what happens for the other situations if I have a bit flip on the target qubit that commutes through. If I have a Z phase flip before a C0 on the control qubit, that will also commute through. But if I have a phase flip on the target qubit of a controlled NOT gate, then again, this will propagate onto the other qubit, in this case the control qubit, and infect the second qubit. And you see here that these two are essentially the dangerous error propagation processes, of which we have to deal with. And when in the following, when we look at the circuit we'll be using for error correction and for fault-tolerant gates, we have to see what the effect of different errors at different positions are, and we can use these identities to work out what's going on. All right, then let's look at what happens if we now wanted to do the error correction, measuring, say, a single plaquette operator. So coming back to your question, why do we need this ancilla? When we want to measure this 4-qubit Z stabilizer, we will be doing what we did for the 2-qubit code, but now coupling this 4 data qubits to the single ancilla qubit. And now, if we have, say here, the Z error happening on the ancilla qubit between the second and the third C0 gate, what, in your opinion, will be the effect? Say again?
It will look as if you have an error.
Where? 3 and 4, exactly. So it propagates through its first C0 gate here, right? Infects this control qubit, and then the second one. So it will not be visible on the ancilla. That we measure on a Z basis, we can't see any Z flip. But it will lead to a weight 2 error on 2 of the data qubits. And that's uncorrectable. So that means that will, when we run our round of error correction, again lead directly to a failure. So that is the signature of a non-fault-tolerant circuit. Yeah? We work with a code that promises us one arbitrary error is correctable, but we are using the wrong circuitry. A single error at admittedly some malicious position. Yeah? If it happens here, we are okay. It's only a single error that would be corrected. But here at this particular position, it results in a weight 2 error. That means we have to think about smarter ways of getting around this. And this is what has been developed over the last 2 decades or so. And here I just want to give you a flavor of kind of the traditional, or one of the traditional methods of how one can make this now fault-tolerant. And what you saw is that it was a bad idea to take a single ancilla qubit and couple it to the 4 data qubits. A single person that is ill talking to 4 people is not a good idea. Everybody will end up potentially infected. So the idea is here, let's take then a larger ancilla, namely a 4-qubit GZ state, and have that, and forget this dashed box for a moment, where we have this 4-qubit GZ state, and now couple each of the qubits here to one of the 4 data qubits of which we want to measure the parity. That is the idea, and what one can show is that if one does this, then the parity of the operator we want to measure will map relative phase of this GZ state that we can then decode by kind of mapping it on a single physical qubit and measure that. Yeah? With that, we can then from this GZ state extract the plus and minus 1 parity information that we want. So what is this dashed box here then? I mean, we don't get these perfect GZ states for free here, but we have to produce them. And we would be doing so by starting here with a one first ancilla in a plus state and then doing these 3 C0 gates that will take us to this 4-qubit GHZ state. And now the idea is that we verify the correct production qubit to yet another ancillary qubit here. And if they are either both in 0 or both in 1, then we say, okay, that's probably the correct GHZ state. Then let's couple this GHZ state to the 4 data qubits and try to measure them. So why does this make this system fault tolerant? That's the same circuit again. What you see here is if during this GHZ state preparation here, you would have a bit flip error on this qubit here, this would propagate onto 2 qubits, the third and the fourth of this ancilla GHZ state. And if we didn't do anything or worry about that, then those would again result in the propagation of 2 errors onto your data qubit register, something uncorrectable. But now, due to this verification of this GHZ state, pre-verification, we will now catch this error. This error that propagates here onto the 4th qubit, it will also propagate up to this warning qubit, if you like. And whenever this warning qubit tells us, hey, I'm in -1, better, don't trust this GHZ state, restart with the preparation of the GHZ state and do that until you get a GHZ state where this warning or flag tells us, yeah, things seem to be fine. Then we can couple this 4-qubit GHZ state to the 4 data qubits one by one. And with that, we prevent this dangerous propagation of the errors. And then there can still be other errors in the circuit occurring. For instance, simply a measurement error here, meaning that we can never directly trust the stabilizer measurement of one plaquette. But there one can then simply measure the stabilizers several times for this little code up to 3 times. And then one can show that by doing that, one can measure all stabilizers fault tolerantly. And it is guaranteed that as long as there's no more than 1 error happening here anywhere in these stabilizer measurements, we will not incur in a logical error on our logical qubit. So that is how one can make things fault-tolerant. That's called DiVincenzo short-type fault-tolerant error correction. But you see, it's quite messy. You know, it's resource-intensive. You know, we want to measure a 4-qubit stabilizer, 4 or even 5 ancilla qubits, and all this overhead of additional gates. And there's then a recent development that started just a few years ago that is now known under the paradigm of flag-based quantum error correction. A very simple idea where that was realized quite late if you think about it. Namely, where the idea is instead of coupling 4 data qubits to a single ancilla, we could simply take 1 additional flag qubit that we couple here with these 2 additional C0 gates to this additional ancilla qubit, the flag, in such a way that when we have, again, this dangerous error that would result in 2 Z phase flips, this is being caught directly by the flag. Yeah? And then whenever a flag is raised, several things can have happened. Yeah, we can have had the situation where 2 dangerous Z errors have propagated on the data qubits, or it could have been perhaps just a measurement error, you know, here on this. And what one does then is to measure some stabilizers, and based on this flag-based syndrome readout and subsequent conditional measurements, one can sort out whether or not such dangerous error situations have incurred, and that is what leads to fault tolerance. Okay, let me pause for a second and ask whether the idea is clear. Yeah.
So I have a quick question. So the flag procedure, does this result in post-selecting?
No.
No, so we directly.
Yeah. Yeah, we cannot directly correct because we don't know, was it now this error, ZZ, or was it perhaps simply just a measurement error here? But we can then, conditional of this flag being triggered, measure some stabilizers again, and then based on this measurement outcome and the subsequent measurements, we can then deduce, yes, it was this dangerous wave 2 error that we should undo, or no, it was just a measurement error. That's kind of the idea, yeah? But we never abort the protocol. It's deterministic. I mean, there's some in-sequence logic. That's a very good point, yeah? and that's one of the challenges that with all the quantum volume is always put under the carpet. You have, as an experimentalist, you have to be able to measure in sequence, take a decision. If something happens here, a flag goes up, measure this circuit, measure that circuit, right? But if you can do that, and I will show you how this has been done, then you can get this fault-tolerantly. Now, what we did in my group is we looked at different architectures, and here you see the segmented ion traps that have been introduced earlier, where the idea is you have a register of qubits that you can now use to encode a logical qubit, but also you have ancillas to measure as flag qubits and as stabilizer ancillas, and some additional ions that are used for recooling. And in these segmented traps, you can then move really ions around, split crystals apart, even rotate little crystals, and bring them into what is known as the laser interaction zone, where you can do gates on them. And what we did is some modeling of this experimental architecture, really looking into kind of the details, that go beyond these simple noise models that I explained, where one takes into account the phonon degrees of freedom, so that the ions get hot when you move them around, and other kinds of experimental imperfections, the durations of these operations, and so on. And what we did is some simulations to essentially work out whether or not quantum error correction is helpful. Yeah? And this is summarized here a bit in this cartoon. So what we want to see is if we encode a logical qubit, and then it's exposed to some environmental decoherence, and at the end, we want to decode the information and find out, was it one logical state or the other? Question is it useful, like for Frankenstein here, to have Igor as a helper to get his fingers in there and do a round of imperfect quantum error correction? So is this actually helpful or doing more harm, right? And that's, let's say, one of the criteria that one can look at to see whether it is apply a round of imperfect quantum error correction. And what you see here is the results from numerical simulations, where our logical qubit is encoded and exposed for some time to noise. And then what one can compare is with the decay of the physical qubit, as I showed you earlier, and then with the different schemes, where you see this De Vincenzo short-type error correction, but also this flag-based error correction, that then show you that for the anticipated fidelities that our experimental colleagues working with trapped ions, for instance, are aiming at to achieve over in the near future, meaning like the next year or two. This curve of doing actual error correction is above the quality of storing information in, say, a single physical qubit. Okay, then let's look at how this works really in an experiment. I find this still amazing. So some years ago, we drew this with PowerPoint, this take your qubit to the left, bring it into the laser interaction zone, and so on. But then we found experimental colleagues at the University of Mainz, in Ferdinand Schmidt-Kahler's group, who were brave enough to actually do this. Here, exactly according to the scheme I just introduced to you. And this is kind of what this sequence looks like, yeah? So they start with, let me go back perhaps. They start with the ions in different areas of the trap, then bring some ions together. Here, for instance, the stabilizer ancilla qubit with the first data qubit that has to be brought here into this laser interaction zone where a gate is applied. And then this crystal is split apart. Another qubit, in this case the flag qubit here, is brought in to do the next C0 gate and so on. So it's really kind of a crazy movie if you think about it. But they were able to pull this off and get this going with a single shot parity measurement fidelity of this 4-body operator that is above 90%. And interestingly, it's also above the level of performance that you would get if you don't use the flag qubit. So it's not yet at the level where this building block alone, if we put it together, will lead to a full useful operation on a logical qubit, but it's already better to use this flag, this additional qubit, and the additional 2 C0 gates than not using it. The first signature of the usefulness of doing fault-tolerant circuits. Then, roughly at the same time, Honeywell Quantum Systems, or Quantum Solutions, and now Continuum, also worked on the 7-qubit color code. This is an effort led by a former postdoc, Kieran Ryan Anderson, in my group, who now is leading the quantum error correction effort at Honeywell. And what they did is they took the entire 7-qubit code with 10 data qubits, so that they used as ancilla and data qubits, and then some additional coolant ions of a different species in a segmented trap where they had access to actually 3 different laser interaction zones. So kind of this movie that I showed you, but now really operating full error correction cycles on this 7-qubit code. And here is a high-level summary of the fault-tolerant schedule. I will zoom in a second. So the idea is that a flag-based scheme is used to measure in the first step 3 of these stabilizers. And then if all looks good, one moves on to measure the other 3 of the stabilizers and then repeats this. And whenever some flag qubit indicates a -1, it lightens up. Then one has to actually remeasure the stabilizers, and this one can then do without using flag qubits with a simpler circuit, and then use this combined information to find out what most likely has happened, and then use this to correct the state. And this correction can be done, if you want, by a Pauli frame update, which is just a fancy word of having kind of a table where you write down what the errors are that you think that have happened on the system. So if one zooms in, here you see a little bit more of this structure. So this is a flag-based circuit where the idea is that, for instance, here you see 4 data qubits coupled to this first ancilla. And the trick here is that one can measure 3 of the stabilizers in parallel, where the other ancillas act as flag qubits for the respective syndrome measurement here, and do this kind of in parallel. That's quite a nice development. And then you see here that for the circuit for the other stabilizers, and here when any of these qubits indicate that something has happened, then one remeasures the stabilizers here with a single physical ancillar qubit. And this is what they did for a number of rounds. And as I mentioned already earlier, the idea of this is that whenever here something lightens up, one uses this additional measurement to find out, was it actually a dangerous error, or perhaps simply a measurement error somewhere here, but on the data qubits everything is fine. And what one can prove is that then one of these cycles, that's the impressive thing, is that if anything goes wrong on any of the components, any of the C0 gates, as long as it's only one component here that fails, this error will be picked up and will be corrected. And so that is what makes up the fault-tolerant character of this protocol. Okay, here's experimental results of up to 6 of these fault-tolerant quantum error correction cycles, where they prepared different logical initial states, and then they looked at how the logical error rate now evolves over time. So first of all, you see, okay, you do more and more error correction cycles. There will be more and more errors, so that's something that is actually generic. Yeah, you never get better with doing longer, but you can just kind of slow down, let's say, how things decay. And what they found is a roughly 2% error rate per cycle. And this is very similar to what you saw in Christopher's talk, who talked about the other 3-qubit code that I introduced to you, the surface 17, that was realized with the superconducting qubits, where Christopher explained how this was done with the 9 data qubits and 8 ancillas on this surface 17 chip, where they found also an error rate of about 3% per cycle, that is close but not yet quite above the break-even point of beneficial error correction, if you like. So what you see here, for instance, is that by doing these rounds of up to 16 rounds of error correction, you see that logical information decays at the time constant of, say, 16 microseconds or so, whereas a physical qubit still lives on the order of 60 microseconds, so there's still a factor of 3 or so in there, but with moderate improvements, as Christopher explained, both on the for trapped ions. One is very close to getting above this level, where applying rounds of error correction is beneficial. Okay, with that, let me pause for a second and ask whether you have questions on the part on fault-tolerant error correction. Yes?
Why does the plus I and minus I states decay faster than the, or like, show this graph with, this one? Why is it worse for the green curves than the other?
Okay, so I think what one has to do is one has to look at the noise. So, I mean, what you there's another plot where they compared this with simulations. I think they find quite a nice agreement. The reason, I think, is mainly that these 7 qubit states, you have to look at them, how they look physically, and they will be exposed to physical dephasing and potentially also correlated, spatially correlated dephasing. And these different logical states, they simply decay differently under dephasing noise in particular.
Shouldn't it be similar to the right one, the plus-minus state, or?
Okay, why here now the green? Yeah, I mean, okay, why you have here a difference and whether that's significant? I would have to look into the exact structure and the paper too. Yeah. But I think what is clear, hopefully, let's say, is that there are some logical states that are much more vulnerable to noise as others. Think of the 3-qubit code. If you just have a logical 0, it will not decay at all qubits in 0. If you have a logical plus, all 0 plus all 1, that's a GHZ state, that will dephase. Yeah, so that's kind of what is behind this, but the state is more complicated. All right. Yeah, then let's go one step further and look a bit into now how we can not only try to extend the lifetime of a logical state, but also do now logical quantum gate operations. And I want to explain to you some experiments that our colleagues in Innsbruck did together with our group, and very recently where they used a trapped ion quantum computer that is now not looking like a messy lab anymore, but it's actually already almost portable, so to say. It's in these 2 19-inch racks. What we did is to prepare logical states and then also run logical gates. So for the logical state preparation, we started in some physical simple state to prepare, and then did this circuit of 8C knots. The details are not so important. And if everything works right here, we would again prepare the logical 0 as before. But now, you see, if there's a single bit flip, say here, we encounter the problem that we've discussed now a number of times. A single error in the encoding procedure would lead to 2 errors on your data qubits that we would confuse with an error here on this other qubit, leading directly to a logical bit flip. So how can we circumvent this? Well, the idea is to use this flag-based paradigm, namely to couple a number here, 3 of the data qubits, to an additional flag qubit in such a way that whenever such a wait 2 bit flip error occurs, it propagates to the ancilla, triggers this flag qubit, and tells, hey, there might have been this dangerous wait 2 error. You should not trust this logical encoded state. But restart your procedure, reset your qubits, and try to prepare this logical 0 state again. And then when this flag tells you it looks good, then you are guaranteed by the circuit construction that no single error, no matter where it happens, can lead to an uncorrectable error. That's the promise. And this is what it looks like in experiment. So you see here the occurrence of the different error events, where 0 means that there are no bit flips on this logical 0. And the orange bar is what you get when you just do this non-fault-tolerant state preparation. And then you see that there's some components where you have single bit flips. That would be something that's okay, that's correctable. But you also see that there's a substantial fraction of wait 2 bit flips that would directly lead to a logical failure. And now adding this verification circuit, you see that by that you extremely suppress this occurrence of wait 2 errors. Those are, single errors are not allowed to lead to any failure anymore. These are sorted out. And only in the unlikely event that you have really 2 errors happening in the preparation procedure, that will still lead to a slight fraction below 1% or so of uncorrectable errors. Again, what you see here is that using this fault-tolerant, more complicated scheme is actually better than using the non-fault-tolerant scheme for this encoding. All right, so with this we have now done better than we did in 2014. by having prepared fault-tolerantly a logical 0. But now, as I promised to you, we actually also want to do logical quantum computation on our qubits. And what you see here is now how we did this. The goal is to apply now a Clifford gate operations, and here you see the single qubit Clifford gates, ZX, the Pauli, Hadamard, and the phase gate, together with a 2-qubit CNOT gate that generates the Clifford gates. And pictorially, you can think of them as gates that allow you to do not 90 or 180 degree type of things on the Bloch sphere. You get to these 6 cardinal eigenstates of the Pauli logical operators. So how can one do these gates? One nice way of doing them is by so-called transversal gates. So a transversal gate means that if I want to do a logical, say, Hadamard gate on my encoded logical qubit, I'm allowed to do so by just doing physical Hadamards on each of the data qubits that form my logical qubit. So that's quite remarkable if you think a bit about it, that by just doing the single physical qubit operations, you get the correct behavior at the logical level. And one important feature that you directly see is if anything goes wrong with the small probability p on any of these single qubit gates, it will at most lead to one error on one physical qubit, rather than messing up the entire 7-qubit register. So fault-tolerant gates are transversal gates are fault-tolerant by construction. And this transversality is really a non-trivial feature. It's not given in general for arbitrary codes. Just to convince yourself, perhaps, briefly, is think of the 3-qubit code. If you just took the logical 0 there and try to do 3 Hadamards, you get this product of plus states. That's not the logical plus state. That is the GHZ state. You see that it's a specific property of the codes, and the nice property of the color codes is that you can do the entire group of Clifford operations transversally. And this is what you see here. After the preparation of the logical 0, we could now apply physically on each of the 7 qubits the corresponding physical Clifford operation that would prepare now our logical qubit in any of the 6 logical states that you see here. And again, by using the fault-tolerant preparation and then the Cliffords, this allowed to prepare these logical states with a fidelity of roughly 99, logical fidelity of roughly 99% or so. So now that we've done a single Clifford operation that's not yet universal, but it's already quite a lot on a single logical qubit, how could we do a logical CNOT gate? And the idea here is that for the CSS codes, which are codes where you have X and Z stabilizers separated, and the codes that I explained to you, they are of this type, one can realize a CNOT in a transversal way. And transversal now means that I take each of the data qubits here, say data qubit 1 of the first code block, couple it with a physical CNOT gate to the data qubit 1 here of the other block. And you can think of this as a layered kind of architecture, where you have 2 codes here stacked on top of each other, if you like, and we're doing now transversally these pairs of CNOTs. Why is this fault-tolerant? Any idea? That's my claim, that this transversal CNOT gate is a fault-tolerant logical CNOT gate. Exactly. Yeah. If we have one error, say here, yeah, it will only propagate to one other error. So, okay, one error becomes 2 errors, but it's only 1 error on each of the code blocks, right? That was our definition of quantum fault tolerance. Yeah. This remains correctable. Similarly, if something goes wrong on any of the CNOT gates, yeah, affects both qubits. Again, it's just 1 error here and there. So this can be corrected. So, and the important thing here is you see what you need for this is the ability to do these pairwise CNOT operations, and that's something that in an ion trap is possible when you have that ability, or when you have the shuttling or other architectures with long-range interactions. So this type of logical CNOT gate is feasible in these architectures. This is now how it experimentally worked. So the colleagues prepared here a logical plus state on one physical qubit, that's with a 16 ion experiment. Then a second logical qubit prepared in 0, and then if you do this logical CNOT, what you expect is to prepare this belt state, and this logical CNOT is exactly now done in this transversal way. And This is what you find then in experiment, that indeed you now prepare a logical Bell state. So that's first time like on 2 complete qubits to get an entangled state of 2 logical qubits with this logical C0 with a fidelity of 75%. And that is obviously not the fidelity that you have when you want to prepare a physical Bell state, on the order of 99%. All right, so with that we've shown here that we can do the entire Clifford group of operations. Now, in order to run quantum computations for any application that allows or promises a speed up, we need to go beyond Clifford, because this Clifford, any quantum circuit only involving Clifford, can be efficiently simulated classically, cannot provide you a speed up. So we need one more gate that is non-Clifford, and that if we have that, then we can realize universal logical quantum computation. Now the bad news is that there is no quantum error correcting code where one can do a universal gate set in a transversal bitwise way, as I explained to you. So that means we need to find some other way of doing this non-Clifford operation. And this is what I want to explain you on the next slide to give you an idea of how one can get now this one non-Clifford gate that is a T gate by other ways, namely by what is called a magic state preparation and injection. So what is this T gate? It is doing a 45-degree rotation about the z-axis. And if we have that, we can essentially reach, together with the Cliffords, any point on the single qubit Bloch sphere. That's what gives us the universality. So how does this magic state injection work? Let me try to go slowly through this. So imagine that our goal is that we have here a logical qubit, and we want to apply a procedure where at the end we get here T psi out, that we apply a logical T gate onto this logical qubit. And the trick is that what we need to do for this as a resource is a magic state, and this magic state here is a superposition state of 0 and 1, which has this kind of angle of e to the pi over 4 in its superposition position. That's where we start here. And then if you do the C0 gate here now between the 4 components, you can work this out. As an example here, the 1, 0 state that will be flipped to the 1, 1 state. So beta 1, 1 should be appearing somewhere here. I guess that's that component and so on. For these 4 components, you can apply the C0 gate and end up, I've written this already in this form here. You end up in this superposition state where I've factored out this ancilla. So after this logical C0, we now measure the ancilla qubit. So what are the possible outcomes if you measure this ancilla qubit? What will happen to that superposition state? What do you think?
Collapses to the initial gate with a T gate applied to it.
Yes, exactly. That is, yep.
The outcome.
Yeah, well, okay, let's see. So if we measure the ancilla in 0, then you're absolutely right. Then the first qubit collapses to alpha 0 plus e to the I pi 4 beta 1. And that is exactly what we get if we apply the T gate to our logical state. So with that, we have teleported this relative phase from this magic state. We've teleported this phase onto the relative 2 components of our logical qubit. That was the lucky day.
Yeah, you have the minus sign.
Exactly. On the unlucky day, when you project it onto 1, now we see, okay, we've kind of not done a T gate, but we've done a T dagger gate. Yeah? We have the wrong phase here. In that case, what we do is we apply a phase gate that imprints a relative phase of pi over 2, and that would take then that state also to that state. And the point is that this phase gate, as we've seen, this is a Clifford operation. We can do that transversally. So that's a simple correction that we can do. So that we have a 50 chance here of either projecting onto 0 and 1, but we can in both cases make sure that we deterministically then inject this magic state and come out with deterministic application of the T gate. Now, yeah.
To obtain this magic state, it seems like you also need to apply a T gate to it.
Yes, yeah, exactly. So I've been cheating, right? I've exactly taken this magic state. That's what we get at now. How do we get the magic state? How do we get it fault tolerantly? And we cannot do the magic state easily so the recipe that was, or the standard recipe is to take, you take your physical qubits, you do a simple circuit that produces on single physical qubits here copies of a physical magic state. And then what one can show is that by only Clifford operations, one can realize what is called magic state distillation. And the idea is that one does one procedure where one ends up then with a magic state on a logical qubit that has hopefully a fidelity that is higher than the fidelity of these non-fault-tolerantly prepared magic states. But you see, this is a costly approach, distillation, because we have to have many copies, and of those we get only a few copies, and of those few copies perhaps one really good copy, and you throw away really a lot, or you need large resources to start with to do this distillation procedure. And that is what really dominates, using this approach, the overhead in doing universal fault-tolerant quantum computing. Eventually, what we need are magic states with extremely low error rates, on the order of 10 to the minus 12, 10 to the minus 14, to do, say, Shor's algorithm in the very, very long run. But what I want to show you is that there's a new approach of how one, again, based on flag qubits, where one can get rid or get around, at least at the lowest level, this need of distillation. Yeah? Because for that, you see, you need here a bunch of logical qubits, and we don't have a bunch of logical qubits yet. So the idea is that we want to get this magic state using a flag qubit-based paradigm. And what I will show you is a T-gate that is not the standard T-gate, but it's instead of the Z direction, we wrote it about the Y direction. But then you see a very similar injection circuit with a controlled Y gate, a measurement, and a correction will lead to a T-gate. Now, we come exactly to your question. So how do we get this encoded logical magic state? And this magic state here that we will be using for the realization of this T-gate is a state that is an eigenstate of the Hadamard operator. So it lies exactly here in the ZX plane at 45 degrees. So the challenge is to get this magic state and then to inject it in a fault-tolerant way. Okay, this is how it works, and this is what the colleagues did in the experiment. So we start by taking one logical qubit and prepare this magic state non-fault-tolerantly. So what you see here is here's one qubit, you can hardly see it, that is in a physical magic state. And then we do this sequence of C0 gates to take that into our logical magic state. However, as before, errors can happen. In particular, imagine that error happens right away on this magic state here. Then we would, rather than encoding this magic state, perhaps encode the opposite magic state. That's why now we need some verification stages. And one operator that we need to measure is the Hadamard operator that can be measured and realized transversally in the 7-qubit code by coupling this to an ancilla again with flag qubits. And what this verifies is that we indeed have prepared this +1 eigenstate of the Hadamard operator. And then what we do is a round of error detection by measuring exactly what I showed you in the Honeywell experiment, each of the stabilizers in a fault-tolerant way a single time, and only if all these ancilla qubits tell us we are fine, then we accept this magic state. And this is a fault-tolerant preparation then where one can verify that no matter where, again, a single error happens here, a single error will not lead to an uncorrectable error on this magic state. This is what happened in the experiment. So where this magic state was prepared. And you see here the infidelity of the logical state after the different stages. So if one just does this simple circuit here, non-fault-tolerant, we have error levels on the order of 10%, but then if one includes these verification stages, the logical error goes down to about 1%. And you see here the logical density matrix, if you like, for this magic state, where you see that that's exactly the density matrix that corresponds to a superposition of 0 and 1 with these relative weights and phase. Okay, so that is now the preparation of the magic state, and then what we did is then to use that magic state, prepare a second target qubit, and realize the injection that I showed you before here. And that is a very complex circuit here of this number of gates. And I told you it requires this in-sequence measurement, reset, and conditional logic. And what you see here is then the results for the injected T gate for different input states and a logical T-gate process fidelity that tells you how, on a logical level, this T-gate works, with which fidelity that works. All right, so with that, I hope I've been able to show you a first universal gate set. It's the first time that a universal fault-tolerant set of logical gates has been realized on 2 logical qubits. It's really a big, important step towards universal logical quantum computation. Yeah, with that, let me, if I still have like 3 minutes or so, then let me just rush very quickly through some of the alternatives, to only give you a cartoon version of what the next steps might be regarding to going to scalability. One is lattice surgery. Yeah, when we published a paper on this, we got this invitation by the Scholarly Journal of Surgery to submit our paper there. Lattice surgery is a bloody business, but not that bloody. And the idea of lattice surgery is a bit that, that when we have a surface code architecture, we want to work in 2D, and we cannot do these transversal gates, CNOT gates that I showed you. So we need another strategy. And this is based on this little quantum circuit that I want to show you how it works. So the idea is to have 3 logical qubits, say our surface code here. And now what one can do is one can look at measuring operators corresponding to both logical qubits jointly to merge this into joint codes. Now, this is what is done in this first step here. Then one measures operators here jointly to merge those, and finally measures, say, this intermediate auxiliary logical qubit to decouple this. And what one can verify that is that overall this will realize a logical, it's again a teleportation process, a logical CNOT gate between one control logical qubit and a target logical qubit. Now you see that this is now purely 2D. We have these patches of code in purely 2D, where we can merge them at the boundaries. That's the surgery operation, if you like, and then again decouple them, and with that then realize logical CNOT in a 2D layer architecture. Another way of getting universality is, I've shown you that for the 2D color codes, we could not do this T-gate in a transversal way. We used the magic state preparation and injection. An alternative is to work with other codes. So there are, for instance, 3D color codes for which a logical T-gate can be done transversally, but then one pays the price that the Hadamard stops being transversal. There's no code where you can do everything transversal. But then the idea is that one can take the best of both codes. So what one does, whenever one has a Hadamard, one works in one code where this can be done easily transversally, and then switches in a fault-tolerant way by deforming this into the other code. In that code, a T-gate can be done transversely, and then one goes back and forth. And this is a way of how one can get a universality without the need of magic state injection. All right, then we have to eventually grow the systems beyond the distance 3 codes, so that, for instance, one can work with distance 5 and even larger codes, so that we increase the robustness of the errors. And then there are different physical architectures. This is what you saw already in the talks before, where now different architectures can be used to build really 2D structures in which one could then embed these logical qubits and operate them in a reliable way. Okay, with that, I think I should wrap up, skip these remaining parts. And simply, I hope I could convince you that now this quantum error correction and also constructing a substrate supporting universal logical quantum computation is not that far in the future. It's actually happening now. And I truly believe that fault-tolerant land, so to say, is closer than one might think. It's obviously very hard, but that one has to think about the challenges that are there already today, namely of how one can operate these systems. One has to think, when one builds a quantum computer, have this in mind of what one needs for these additional levels. How would one operate logical qubits? What are the requirements in terms of connectivity of control protocols, characterization, simulation, and so on. So these are many fascinating aspects, both on the theory and experimental side. And if you are interested in joining this effort, we have open PhD and postdoc positions in our group. Just get in touch. With that, let me thank my group and my collaborators for their great work, the funders, and you for your patience. Thanks.
Thank you very much, Markus. Also for you.
Thank you.
Some Swiss chocolate. I hope you'll appreciate it.
Thank
Are
you.
there any questions up till now?
I have a quick question. So, when you showed, for instance, this like Clifford gate to each of the qubits, and then it's like, okay, we can think of a Clifford gate going wrong. But if you think experimentally, that's never what happens, right? Probably you have, I don't know, a control system that applies a Clifford to all of them. And
No.
over-rotates a bit or under-rotates a bit, right?
That would be a that you do the individual pulses so that ideally the errors that happen on those are uncorrelated. Okay. You should not do it with a global, Rabi flop or something.
Okay.
Yeah. Other questions?
I had one small question with the deforming of the codes you just showed a couple of slides ago.
With the surgery?
Yes, exactly.
Okay.
And for me, it was difficult to see whether, like, does there need to be an isomorphism between these two, or how do you easily switch between those?
Okay, the key idea is that this is a type of gauge fixing. So you have, let's say, different subspaces that you fix by measuring different operators. So, I mean, in a nutshell, what you have in this 15-qubit code are some X-type cell operators and Z-type phases. You have these Z phases also in the Steen code, but here on this 15-qubit code, for instance, you don't have these X stabilizers. So you're measuring some operators to another set of operators, and the key is, in this measurement, when you do the switching, the logical operators do not change, or the logical states remain preserved. So it's choosing a different gauge, so that you go from one gauge to another, and the different gauges allow you to do different logical gates in different ways. Yeah, sorry, there's only a cartoon. I didn't have time to go into this with more detail.